Okay, so we've seen in diagonalization that if you have an n by n matrix, if there is a basis of eigenvectors, then A can be diagonalized. And so what that means is that there's going to be a diagonal matrix D where the diagonal is A's eigenvalues, and an invertible matrix P whose columns are A's eigenvectors. So that A is equal to PDP. All right, so we're going to compute one of these by hand, and then I'll show you how to do it with Sage, which is a lot less lengthy. So to begin with, we need to find what our eigenvalues are and our eigenvectors. Okay, so to find our eigenvalues, we're going to look for our characteristic polynomial. So we look for the determinant of A minus lambda I. What that means is we're subtracting lambda from our diagonal elements. Okay, so we calculate this determinant. Okay. Multiplying this out, we find negative 30 minus 6 lambda plus 5 lambda plus lambda squared plus 30. And notice this negative 30 and positive 30 cancel. And so this is negative lambda plus lambda squared. And we can factor this, right? So we get lambda minus 1 times lambda. So the eigen values are going to be the zeros of this polynomial. And so we see that there are 2 of them. And they are lambda equals 1 and lambda equals 0. Okay, so once we know our eigenvalues, then we can find our eigenvectors. Right, so these are going to be solutions to A minus lambda I times V equals a 0 vector. All right, so let's do this first for lambda equals 1. So A minus lambda I, we're going to have negative 6, 10, negative 3, 5 times the vector B gives us the 0 vector. So that tells us we've got negative 6x plus 10y, negative 3x plus 5y equals 0. Okay, so we can see pretty easily that the second equality is just half of the first equality. Okay, so that means that negative 6x plus 10y equals 0. I'm going to divide through by negative 6. So x minus 10/6y is 0. So x equals 10/6, or 5/3 y. And so this vector xy is 5/3 y I, or 5/3 y times y. Okay, so one eigenvector that we can use is just this eigenvector 5/3 y. You know what? I want whole numbers. I'm going to multiply everything by 3. So I'm going to use 5, 3. Okay. Next up, let's look at lambda equals 0, our second eigen value. So our matrix here was -5, 10, -3. What was it? -5, 10, -3, 6. Okay, times xy gives us -5x plus 10y, -3x plus 6y. Okay. These guys are definitely multiples of each other. So -5x plus 10y, 0. I'm going to divide everything by -5, so x minus 2y is 0. X equals 2y. And so our solution is going to be 2yy. And an eigenvector here is 2. Okay. All right, so we are feeling pretty well equipped. We have a set of eigenvalues and a corresponding eigenvectors. So our eigenvalues give us the diagonal matrix. So this matrix D is going to have eigenvalues 1 and 0 on them. And the eigenvectors give the matrix P. Okay, so in P, we're going to put the first column is going to correspond to this first eigenvalue. So for lambda equals 1, that's going to be this first column. The eigenvector we found there was 5/3. Oh, 5 and 3. Okay. For eigenvalue 2, which was 0, we are going to, that'll give us our second column here. And this was the vector 2, 1. Okay. We need one more piece to complete our picture, which is that we need to find P inverse. So this is going to be 1 over the determinant of P times we switch the diagonal elements, negate the off diagonal elements, and determinant of P here is -1. So we're going to have -1, 2, 3, -5. Okay, and so we can write this matrix A, which was -5, 10, -3, 6. As this product where we see some good geometric information. So this this first in the direction 5, 3. What does this matrix multiplication do? It just preserves that eigenvector. Everything along that line just stays put. If we look in the direction 2, 1, what happens to our eigenvector? It just gets squished to 0. So the image of multiplying by this map is that we're just going to have a line. All right, so we see that this was kind of a lengthy process. Next, we're going to show how to do this kind of computation using Sage.